think we're going. So, George completed his PhD in pure mathematics in 2015 at the University of Szeged, Hungary. In his thesis, he investigated problems from Hilbert's space-operated theory. Due to this work, he was awarded the National Outstanding Research Award by the Hungarian National Excellence Program. During his postdocs, he worked with problems related to Wigner theorem and grew more and more interested in other areas of quantum physics. In 2017, he was awarded with the GAMAA Ames Award for his solo author paper as the best paper of the year, published in the Journal of Mathematical Analysis and Applications. In 2018, he obtained a Leverhulme Trust postdoctoral fellowship, which he held as a PI for 3 years at the University of Reading, UK. And after finishing his fellowship, he started his current position as a senior quantum scientist at River Lane, Cambridge. His main work now focuses on quantum error correction and fault-tolerant quantum computation. Let us all welcome our speaker.
Thank you very much for the nice introduction, and also for the invitation to give a talk here. So today I will talk about this paper, which is a joint work with Ophelia Crawford and Earl Campbell, both are at River Lane. And essentially, the idea of, or the motivation of this this work was that for the Pauli-based computational model, when we would like to execute fault-tolerant quantum computation with the Pauli-based computational model, we need to measure sort of unusual or irregular shaped stabilizers, which are not naturally measurable on a square grid connectivity device. And that was our main motivation to come up with a method for that. And it turned into a more general method. But the main application we presented in the paper was essentially about this twist defect and elongated rectangle stabilizers, which come up in the Pauli-based computational model for the planar code. So my plan today is to briefly just introduce the planar code itself, how we extract the how we measure the stabilizer-free circuits, some things about hook errors and scheduling rules, how we should schedule the stabilizers so that we end up with a valid circuit. Then I will talk a little bit about the Pauli-based computational model in general and some existing proposals which included hardware modifications. And after that, I will go into the main part of the talk, which will be essentially about breaking the scheduling rules and using this how we can exploit this to measure these non-local irregular shape stabilizers. So I will explain how that works, and then after that I will show you the simulation results we obtained, and I will finish with 2 proposals for fault-tolerant architectures, one with the rotated planar code and the other one with the rotated planar code. So as probably the people here know, the planar code has 2 variants. One is the original GitHub one, the rotated planar code. So here on this picture, we have qubits colored green and black. The black qubits are data qubits where we store the information, the logical state, and the green qubits are used for measuring the stabilizer. So for instance, this green qubit is used to measure the XXXX stabilizer supported on these 4 data qubits. And usually throughout the talk, whenever you see like a red plaquette, it always means an X-type stabilizer, and a blue plaquette will mean a Z-type stabilizer. So this, what you can see here, is a annotated planar code with distance 5. This is the X logical operator supported on these 5 qubits. The Z logical operator is on the left side. And you could also define a non-rectangle shape, but more like a non-square, but a rectangle-shaped annotated planar code where the x and z distances would be different. So I did that for the rotated version, which is kind of gained more and more popularity recently because it has the same distance as the annotated version, but with using half of the qubits, though it's not entirely obvious that actually the rotated planar code is better than the annotated planar code. So there are results in the literature which shows that if you count the QEC performance in terms of the number of physical qubits you use, actually there is not much difference. But certainly this is more popular nowadays. So here you see rectangular shaped planar code, rotated planar code. The z logical operator is here, which has weight 3. So the z distance of this code is 3. And the x logical operator is here at the bottom, has weight 5. So we say that therefore the x distance is 5 for this code. So of course, these notions of the distance is sort of can be defined without defining the circuits with which we extract the syndromes or measure the stabilizers. The reason why you see here numbers is that like these numbers specify how we construct the circuits to measure, let's say, this Z plaquette here. So if you look at this picture here, this number corresponds to this P1. So P1 would be Z in this case. This number 2 would correspond to this P2 here. So essentially, if you have a stabilizer P1, P2, and so on PM, then this is a very natural circuit with which you can measure the stabilizer using one auxiliary qubit. These numbers essentially specify the order of the Paulis, the control Paulis you apply. And it's well known that this scheduling, which we chose here for a stabilizer, so like a Z-shaped on the blue plaquettes and an N-shaped on the X stabilizers, so they will maintain the so-called effective distance or fault distance of the code, meaning that the minimum weight, minimum number of fault locations to cause an X logical error is still 5. And the minimum number of fault locations during the circuit to cause a Z logical error is still 3. And the reason is because this is kind of the worst error which could spread to data qubits. So if after the second layer we have an X error on the auxiliary qubit, then if we push this through to the measurement, so the measurement will be unaffected. So by the measurement, we will not pick up this this error here. But because we pull it through the controlled Pauli operators, essentially we transfer errors to the data qubits. And in case when our stabilizer has weight 4, these are the worst case scenarios. So on a Z-type stabilizer, an X error on the auxiliary qubit could spread into a horizontal ZZ weight 2 error up to stabilizer equivalence. And on X-type stabilizers, an X error could spread to a vertical weight 2 data qubit error. But the direction of this X error is orthogonal or perpendicular to the X logical operator. Therefore, this doesn't reduce the effective distance. It's still 5 for X. And also because this is horizontal, but the Z logical is vertical, they are kind of perpendicular to each other. Therefore, even though we have 2 data qubit errors caused by just one fault location, the effective distance or the fault distance is still 3 for this code. So that's kind of why this scheduling is a popular one. And usually this is what we aim for. So if we have a code, we would like to find a schedule which maintains the effective distance or at least decreases it as little as possible. So both planar codes can be sort of executed on a hardware, on let's say a superconducting hardware, where we have this natural square grid connectivity. So this one is very, very natural choice for the annotated planar code, and this rotated version is very natural choice for the rotated planar code. Okay, so let me now introduce the scheduling rules. So, of course, if we have an X stabilizer here and let's say a Z stabilizer here, then if you just concentrate on this X stabilizer, it doesn't really matter in terms of like validity of the circuit what scheduling we use here. Also, separately, if we consider the Z stabilizer, it doesn't really matter what scheduling we use here. It will always give us a valid circuit. But this is not true anymore if we want to parallelize the circuit. So if we want to measure the stabilizer simultaneously with a low-depth circuit, then ideally we would like to just execute this in 4 untangling layers. And so from this paper by Litinsky and von Oppen, we know that, for instance, from this paper, we know these scheduling rules. So if you look at this picture here, every data qubit lies here at the corner of square plaquettes, and the A, B, C, D. These are the layers, so similar to here. And of course, one rule is that every qubit should be so for every qubit, these A, B, C, D numbers should be different, because in one layer you cannot act on the same qubit twice. And this is the scheduling rule scheduling rule A, which just essentially formalized like this. And there is the other condition, which is a bit more complicated. This essentially means that for every pair of distinct circuits, so like let's say there is a circuit for this one and there is another circuit for this one. So if we simultaneously execute them, so parallelize the circuits and execute them simultaneously, then this should be equivalent to execute them one after the other, essentially. And this turns out to be equivalent to this scheduling rule, which means that let's say if these are the A, B, C, D numbers, so either A is less than B and C is less than D, or the other way around. And you cannot have this because then the circuit will not work. So you cannot have that A is, let's say, greater than B, but C is less than D. So you have to have this consistency with this greater signs here. And why is that so? So the reason why you can see that if condition B is satisfied, then the parallelization of all the circuits in the code will give you a valid circuit for measuring all the stabilizers simultaneously and independently is kind of illustrated here. So what you can do is that you just take all the X-type stabilizers and the Z-type stabilizers, and you kind of try to regroup the controlled X, controlled Z gates, so that all the controlled X gates, let's say, happen before the controlled Z gates. And if you can do that without introducing any additional gate anywhere, so you can regroup them in that way, then you can easily see that it's essentially, in that case, the circuit is equivalent to just measuring first the X stabilizers, then the Z stabilizers. So in this case, where the scheduling rule B is satisfied, so 2 is greater than 1, 4 is greater than 3, then let's say if we regroup just the 2 controlled gates which are targeted on this data qubit, then this is what happens here. So these are the 2 auxiliary qubits. This is the data qubit there. So there is controlled Z because it's in the first layer. There is then controlled X in the second layer. And then you just want to pull this through so that controlled X is before controlled Z. But you have to pay the price that you then entangled the 2 auxiliary qubits, even though you didn't make this, you didn't perform this gate. It's kind of, you have to include it there. It's kind of implicitly imply that you have to put it there so that the equation works. And so in this case, let's say we have 2 such data qubits where this is true. So you would also do the same for the dashed case here. And therefore, you would have two control z's between the auxiliary qubits, which would cancel. So therefore, you could see that, yeah, essentially for these two stabilizers, you can just first do the control x's and then the control z's and then measure out the auxiliary qubits. So this is how you can see that condition B is essentially a needed, is a necessary condition for the validity of the circuits. It can be also proven that these two conditions are actually equivalent, but I'm not going to go into the details here. They are discussed in that paper. So next, I would like to talk a little bit about the Pauli-based computational model. So usually, this is a very popular model for let's say, evaluating how costly it would be to execute an algorithm using the planar code. So what happens is that we have a circuit which we compile into Clifford plus, let's say, T gates or pi over 8 rotations. And so let's say you obtain a circuit like this here. So this is from Litinsky's Game of Surface Code paper. So we have this circuit, which we, using some rules showed here, can transform into a circuit where you have just pi over 8 rotations, possibly multi-qubit pi over 8 rotations, then some Clifford operators, and after that, some Z measurements. And then you can even transform this if you push this into the measurements, then essentially you end up with pi over 8 rotations and multi-qubit Pauli measurements. And as you can see here, all any of these pi over 8 rotations, so any of these green boxes here, can be transformed into a multi-qubit Pauli measurement when you have to initialize here a magic state, a T state, a 1-qubit X measurement, a Clifford correction, and a Pauli correction. So essentially, every circuit which is compiled into Clifford plus T can be executed as a series of multi-qubit Pauli measurements, and preparing some magic states. So because of this, there are certain things which we have to keep in mind. So for instance, how we do multi-qubit Pauli measurement is with the method called lattice surgery. So I'm explaining it here. We have essentially two planar code patches. And I also laid here a background lattice on essentially behind the patches. So every qubit on the hardware is either at the vertex of or the corner of some of these plackets or in the middle. And typically the ones in the middle are used for auxiliary qubits, and the ones on here are used for storing information or for routing. So we laid two patches on this hardware, and they are kind of aligned with respect to the background lattice. So which means that all the red plackets are on top of white squares, like also here. And the blue plackets are on top of this gray plackets, also here. And if this is the case, and we were to measure X-logical tensor X-logical, then it's kind of easy to do that using only local stabilizers. So by local stabilizer, I always mean that it's a stabilizer we can measure with using just one auxiliary qubit on the square root connectivity device. And this is how we do it. So we kind of measure the stabilizers for some rounds. We initialize in the last round the data qubits here in between the patches. Then measure the stabilizers of the long patch for the number of rounds or proportional to the number of rounds. And then we measure after that the stabilizers of the two patches and measure out also the data qubits here in between. And this performs an X tensor X measurement. So if we were to measure, let's say, Z tensor Z, then we could merge in a with a U-shaped patch, using also, again, just local stabilizers. And the crucial reason why we can do that is is seen by a coloring argument. So when you want to obtain the X tensor X logical outcome, you have to multiply together these purple outcomes. And you can see that they kind of are always on top of the same colored squares. So they kind of follow a checkerboard pattern. And if you were to measure Z tensor Z, then these outcomes would be on top of the grays one instead of the white ones. But like you are here also, so you can easily kind of see that like this consistency can be kind of kept. But if you were to measure, let's say, X tensor Z, then that would be a problem, because you would like to have this outcome, which is on top of a gray square, but also would like to have this outcome, which is on top of the white square. So just using local stabilizers, you cannot measure X tensor Z in this case. There is a method to do it, of course, but you have to use this long-range stabilizer. So let's say this one here is a weight force stabilizer, which is supported on these 4 qubits. And you somehow measure them, let's say, using these 2 auxiliary qubits. But it's a non-trivial task how to do it on the square grid connectivity device, which is the reason why previous proposals mostly considered hardware changes to measure these stabilizers. So the situation is even more complex if you have a Pauli measurement which involves a Y-Pauli term as well. Then you need to use twist defects as well, which are weight 5 stabilizers. I will introduce them later. But now let me introduce you the previous 2 proposals for doing fault-tolerant quantum computation, which involved hardware modifications. So the first paper, which did it and also took into account the hardware constraints, was this paper about twist-free lattice surgery by one of the authors, Earl Campbell and Christopher Chamberlain, who is Amazon. And essentially what they did, they proposed a twist-free lattice surgery method. And it works like the following. So you have the logical patches laid out on the QPU on the hardware this way. So you have some routing space to do the lattice surgeries. And let's say we want to measure X tensor Y tensor Z tensor Y. Then what we do is that like we have this, first of all, this dislocation area here, which is a modification of the hardware. So here on the left side, so you can see that, let's say, these yellow qubits are connected to the adjacent black qubits diagonally. So it's almost a square grid connectivity device, except here, where you kind of have these black dots, black qubits, kind of not in the locations where they should be. And also there is just only one, but these are connected almost diagonally to these 4 qubits. So this dislocation area is needed because here you can measure an elongated rectangle. And what they proposed is that, like, okay, we have this X, Y, Y, Z. Let's initialize a 0 auxiliary patch. And we will use this for the elongated rectangles. So once we initialize this, the next step is to pick those 3 patches, which are either X or Y. So these are the 3 patches here. Let's do XX lattice surgery between these 3 patches and the auxiliary patch. So they are all connected at the X sides. And after that, let's pick those 3 patches where we either have a Y or a Z. and let's do a Z X lattice surgery. So because it's a mixed type lattice surgery, we have both Z and X, we need the elongated rectangles, and that's why we have the dislocation area. After this, we would measure out the auxiliary patch, and then that would essentially perform the X, Y, Y, Z logical measurement, which we wanted. So this is the first proposal called twist-free lattice surgery. This means that, like, for every Pauli multi-qubit Pauli measurement, we need 2 lattice surgery operations. So that is like a time overhead that you have to spend twice as much time doing this lattice surgery doing this multi-qubit Pauli measurements. But as compared to the case when you don't care about the connectivity constraints, but like here they took into account the connectivity constraints. So it's more realistic to kind of execute this one than the other ones where you don't consider the hardware constraints. The other proposal is, again, from the same authors. They proposed twist-based lattice surgery. And here is where you need twist defects as well. So again, we have 2 patches and some routing space in between. And if we want to measure Y tensor Y, then kind of we have to construct a merge stage patch for lattice surgery, which connects the 2 patches along both the X and Z sides. So as you can see here, this is the X side, this is the Z side. So the merge stage patch connects both sides of both patches. But you need elongated rectangles and also the twist defects. So a twist defect is a weight 5 stabilizer. In this case here, this should be Z, X, 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 and Y. So typically we have Y in the middle here, and like X or Z on the sides. So for this proposal, they came up with a uniform connectivity hardware proposal, which you can see here. So you have the usual square grid connectivity hardware, but you introduce additional horizontal connectivities, which are the brown lines here, so that you can measure the elongated rectangles and the twist defects. And here the numbers essentially just tell you in which layer you execute which entangling gate. So while this is a proposal which does fault-tolerant computation with the planar code via the Pauli-based computational model on a uniform connectivity hardware, the degree 6 which it requires is probably, at least as of the current state of hardware now it's very high. So usually, as far as I know, the best hardware in terms of connectivity is weight 4 is the square bit connectivity device, which is actually existing at the moment, and it seems to be like engineeringly very challenging to introduce more connectivity. Okay, so just to recap on a few things before I go into the
I have a question. So could you go back to the 2 slides? Go back 2 slides. Okay. So I'm a bit lost. Maybe so this surgery is for you to do some error correction. Like say, so I have an initial state there, then I just distribute my my physical qubits to some patches. And if I want to correct some X error, then I have to surgery connect them to that patch. So what does this surgery do? I'm not so sure.
Okay. Yes. So if I go back to this part, so kind of we are considering this picture where you have to essentially measure this, let's say Y, Z, Z, Y, X, X, and so on, multi-qubit logical Pauli operators, and you do it by lattice surgery. So here I just showed how to measure X tensor X, for instance. So let's say for this case, and this proposal of Christopher and Earl essentially describes how to do it for a general multi-qubit Pauli operator on this hardware. So here what you see is that like you have some logical qubits encoded into these patches, and you are to measure X tensor, Y tensor, Y tensor, Z. And this is the proposal to do it. Does that make sense? Or
but you say each page is a logic qubit? Already?
Yeah. Yes.
Then okay, but then what does it mean? Like you put a Y or X on it, then
yeah. Okay, so it just means that like this process in B, C, D, the result of that will be to measure X logical, Y logical, Z logical, Y logical.
but you say like each of this page is already a logic qubit, so then you connect to it. Then but
yes.
What's the difference between each page?
Well, I mean, so if you, for instance, let's say we have this very small circuit with 4 logical qubits, then each patch would be, let's say this would be one patch, this would be another patch, and so on. And let's say if you wanted to measure this one, because this is how you transform your circuit, then that would mean that like on the first patch I would like to measure Y, on the second Z, and on the third one Z, and on the fourth one Y. And if let's say this is 1, 2, 3, 4, and that would be a Z here, then you would measure this Y, Z, 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 Y in that case. So it's really just
so can I understand like so this also here these pages is not just logic qubit, it's also the operations like the full circuit picture you encoded here.
Yeah, exactly.
Okay.
Yes.
Okay.
Yeah. Maybe I should have said that. Yeah, like every patch is a logical qubit in the circuit. So usually we start with maybe if I go back again to make this clear. Yeah, so we start with like just a logical circuit which is compiled into this T gates, Clifford. Oh yeah, Cliffords are the orange gates, and 1 qubit Z measurements. So this is very common to compile a circuit into such a gate set. Then after that, you transform it into essentially such a circuit where what you have is that like essentially a series of multi-qubit Pauli measurements and some Clifford corrections and Pauli corrections. But essentially, these are the main ingredients in your computation. So you always measure these sort of multi-qubit Pauli operators. And you then just on your hardware allocate for each of these qubits a planar code patch, and then you just do these measurements essentially to execute your computation. So in this case, they laid out the patches in this way, and whenever in the circuit our next measurement is to do X, Y, Y, Z, or any Pauli measurement, then this is how we would do it. So it would be the first lattice surgery operation would be purely X-type lattice surgery, and the next one, the last one, the second one would be a mixed ZX-type lattice surgery. It should be X on the auxiliary patch, but on the other patch it should be Z. Does it help? Does it explain your question?
Yes, thank you.
Yeah, no problem. If any more questions on this proposal or the other one? Okay. If not, then I will continue with the next slide. Just to recap on what happened so far. So if we design a hardware, at least this seems to be the case for all the existing hardwares, what we really would like to have is a low degree connectivity hardware, usually 3 or 4. So this is a very natural choice for many reasons, because then if you have a uniform hardware, then you didn't tailor it for particular codes with particular code distance. So you have more freedom essentially to execute different codes. But increasing the connectivity would increase crosstalk noise, for instance, and it seems very very challenging. And obviously, if we have, like, let's say, a degree 4 connectivity device like the square grid connectivity device, that naturally limits the weight of stabilizers which we can measure locally. So, like, by locally, I always mean that we have one auxiliary qubit we can allocate for a stabilizer, which is connected to it. So on a square grid, this weight is maximum 4. And just in general, there didn't seem to be a general technique available to measure long-range stabilizers, like the elongated rectangles on a square grid connectivity device or the twist defects. So this was our motivation, and this is what I will explain now in the next few slides, how we can achieve this by violating the scheduling condition. So for the surface code, I sketched briefly how the Pauli-based computational model works by measuring a series of multi-qubit Pauli operators. And so for this one, we needed twist defects and elongated rectangles. But however, I would like to mention that there are other alternatives to the Pauli-based computational model. So for instance, if you have a Clifford plus T circuit, you could just execute each gate sequentially. And it's not clear in general which one is better. It's probably something which depends on the algorithm you would like to execute. Which one is better to choose, or which mixture of the two is better to choose. So I could imagine that if you have a circuit, then probably in the future, in order to be as efficient as possible, it would be one of the tasks of let's say the computer to decide how to transform this circuit, this Clifford plus T circuit, into a mixture of Pauli-based computational model and the computational model. But essentially, it's not clear exactly which one is better. It seems that if we have fewer magic states, then probably PBC is better. And this is what most costing paper takes into account, because it gives a very simple estimation on the time it takes to execute the algorithm. But if we do the other model, the computational model, then the S gates, Hadamard gates, CNOT gates, and the T gates, so these all can be executed on the square grid connectivity hardware, but potentially could take longer to do it. So yeah, like if you use Pauli-based computational model, then it's not clear how to measure those stabilizers, and I will go into that in the next few slides. Okay, so essentially, the main idea was to that we have these two conditions, and obviously condition A cannot be broken or cannot be violated, because we always want each layer to have each qubit once only. So this is not something we can play with, but we could play with this one. So instead of having this ordering or that ordering, we decided to let's see what happens if we did this tangled or unusual ordering. And this is what you can see here. So if let's say you schedule the X placket and the Z plackets like this, then so this layer comes before that layer, but the other one, the other control X layer, comes after this one. So if you now regroup the control X's so that they happen before the control Z's, then this is the situation. So you pull this through the control Z, but you pay the price of having this entangling gate between the two auxiliary qubits, even though they are not connected on the hardware. So this is a violation of condition B because previously we had this twice, but now we just have it once. So we introduced this control set between the two ancilla qubits. And our thinking was that, okay, let's see, maybe this is actually can be used for something. And it turns out that we can, using this, we can actually measure the product of the two plaquettes. So let me explain how this happens. So if we just take this scheduling and therefore, we apply control X between these qubits and control Z between those two qubits. So we just write out the circuit which this scheduling defines, like the parallelized circuit. So this is the first layer, second layer, third and fourth layer. And then we measure in X basis. So in this case, we will get completely random data because when we regroup the controlled X's to happen before the controlled Z's. So this is then how our circuit looks like. And so the reason why you have a controlled Z here is that so this controlled X can just push into the front. Also, this one can be just pushed because there is no controlled Z's there. But this one, when you push it through, so you have to interchange this one with that one, and that will introduce this controlled Z here. So if someone is interested, you can track through the stabilizer formalism why these outcomes will be random and unrelated to any, let's say, any of the stabilizers. But the point is that we can fix this. And the fix for this case, when we have a pair of such two stabilizers, is to change the basis for the measurement and introduce Clifford correction. So we change the basis here to Y basis. Now we measure in the Y basis. We have the same circuit as before up until this point, which you can also see here. So up until the measurement point, we have the same circuit, but this is different here, the Y measurement, because now it turns out that the sum of the two outcomes will correspond to the measurement of the product, which is this minus XXYYZZ. So weight 6 stabilizer was measured using just the local connectivity of the square grid hardware. But we also have to pay a price that we have to apply this Clifford correction after one round. So the Pauli correction G1, M1 will depend on this outcome. The Clifford, which is this one, it doesn't depend on the outcome. And that's good because if we execute this for 2 rounds, then this will become a Pauli correction, which we can track in software. But let me maybe first just say that I probably won't go into the details, but how you can see that this works is using this lemma or equation. We called it a trimming lemma in the paper, where essentially you have this auxiliary qubits initialized in plus, you measure in the Y basis, but you have this controlled G1 and controlled Z, which would correspond to this control G1 here and control Z there. Then you can kind of get rid of this qubit and essentially based on the outcome you have to put here. Now the control for the G1 is on the other auxiliary qubit. You have to put here a ZM Pauli correction and an S gate Clifford correction, and also a correction on the data qubits to end up with the equivalent circuit. And this is how you can see, if you do this step, you can get rid of this first auxiliary qubit, then all the controls will be here. You will have these Z and S corrections here. But if you kind of go through this, you will see that essentially this is equivalent to just having one auxiliary qubit with some corrections here, and then you just have control G1, control G2, and therefore you measure the G1, G2 product. And as I mentioned, usually a Clifford correction is not something which we like because so either you usually when you have a correction, a Pauli correction is easy because they can be tracked in software, so you don't have to apply the gates, apply like a logical Pauli on hardware. But the Clifford is different. That typically you have to apply on hardware, and this one is a complicated Clifford operator because it's supported on 4 qubits in this case. Sorry, and therefore it's better if we can just forget about this. But this is the case if we do 2 rounds. So this is 1 round, and this is the next round of the same circuit. And so that the 2 Clifford corrections which would come after each round could be combined into just 1 Pauli correction. So if you use this tangled method to measure some high weight stabilizer, then it's always best to do even number of rounds, because then you have a Pauli correction. So it's a slight maybe constraint on the number of rounds you can execute, but if you were to do odd many rounds, then you just do 1 more and it solves the problem for you. And also, even though I will not talk about it here, we can do this for not just pair of plaquettes, but for many plaquettes, many stabilizers. And again, 2 rounds is always enough to have a Pauli correction. Okay, so I'm now going into the part of the talk where we measure the twist defects and the elongated rectangles. And so this is how we can measure them. So this is the connectivity of the device, and we would like to measure XXXX or XXYXX. Then what we do is that we initialize the other 1 or 2 qubits in the I eigenstate. Then with the tangled syndrome extraction method, we measure the product of this X type and this ZZXX stabilizer. So that as a result, we measure the product, which is XXYYXX. And because we initialized this in Y eigenstates, we measured the elongated rectangles and the twist defects. So this is how it works. For a twist defect, you can measure, for the twist defect and elongated rectangle, you can measure with this connectivity. And to show you how they perform, let me just recall what is a quantum memory experiment. So quantum memory experiment is when we have this patch. Let's say we would like to test how efficiently it can store the logical 0 state. So what we do is we initialize all data qubits in Z basis. This is why we have them colored blue. Then we measure for some number of rounds. The X stabilizer outcomes are random, but the Z stabilizer outcomes are under noiseless execution should be 0. And then if you compare the outcomes from 2 consecutive rounds, they should agree. And finally, you measure out all the data qubits which have random outcomes. But from these 3, you compose the logical observable, which would be a logical operator here. So based on these outcomes, you define some detectors, which are combinations of measurement outcomes, which would be deterministic under noiseless execution. And these would signal for errors. So if they are not the expected outcomes, they would signal, oh, something happened in the circuit, some error, which we have to correct for. And once you have the detectors, then you can define your decoding graph to do some decoding, and then just decode for this outcome here, which we know should be 0, but kind of this logical observable is something which we use for testing if our decoding works. The X memory would be similar, but we initialize data qubits in X basis and measure in the end in X basis, and we would combine the bottom 3 outcomes into the logical X observable. So this is standard quantum memory, and that is another sort of a dual of quantum memory experiment, which Craig Gidney calls the stability experiment. And this is a very, in my opinion, very useful experiment to estimate the number of lattice surgery rounds, for instance, you need during fault-tolerant computation. So what happens is that you initialize all data qubits in the X basis, then you measure the stabilizers of this patch, which is which doesn't store any logical information because you have overdetermined stabilizers. So the Z stabilizers are overdetermined; they multiply into the identity. And then you do some number of rounds, and then the end measure out all data qubits in X basis. And your logical observable is the joint parity of the blue outcomes, which you know should be 1. But of course, you don't use this information for decoding. This is you to test that your decoding was successful. And this kind of is what it tries to imitate is that like this would be kind of a patch in between the 2 patches during lattice surgery. So you would multiply in the outcomes in this way, and this is why it's a good test for getting an idea about how many rounds of lattice surgery operations you need, how many rounds of syndrome extraction you need during lattice surgery. So essentially, we perform numerical simulations on the default rotated planar code patch and the tangled version. So these 2 patches, for instance, they both have X effective distance 3 and Z effective distance 7. So what happened here is that we exchange these stabilizers in this row into tangled syndrome extracted stabilizers, so elongated rectangles, but using tangled syndrome extraction. The line in between tries to indicate that like these plaquettes are tangled, and therefore this actually measures Z, Z, Y, Y, Z, Z, and we initialize this in the Y basis as before. So we need to pay a little price that like the height of the patch is the same, so the Z distance doesn't change. But if you include these tangled elongated rectangles, then the horizontal distance, the X distance in this case, so this one, is almost halved. So this is why you have almost double wide patches here, because like here is the X logical operator, and from this ancilla qubit, because these are not data qubits anymore, the X error can spread horizontally. It doesn't really matter which plaquette you use. And this is something which we have to compensate for when we propose the fault-tolerant architectures. But essentially, maybe I can see that like I'm almost out of time, so maybe I will just quickly show this simulation plot that what we have here is from this simulation data, we concluded that as long as the effective distance of the tangled patch and the default patch matches with each other, we have very similar quantum memory performances. And after the talk, if there are any questions, I can explain more detail. But like essentially, the conclusion is that like with agreeing effective distances, we have almost the same performance. We also did stability experiment for the tangled patches, and so compared, for instance, this 2x2 default patch with this tangled patch where we just replace this row with the tangled elongated rectangles, and also this one was compared to that one and that one where we just replace this row with tangled plaquettes. And we computed the time overhead, which essentially means that this number here is, let's say, I don't know, let's say here for this point, if we are at physical error rate 5 times 10 to the minus 3, let's say here, then for the 4x6 patch, for the default case, if we performed n number of rounds for stability, we need to perform for the tangled version 1.6 times n number of rounds. So this time overhead is like a scalar factor which you have to multiply into the number of rounds for the lattice surgery operations, for instance. So we have data from for physical error rate in between 2 times 10 to the minus 3 and 10 to the minus 2, because we had to use BPUSD to decode, because minimum weight perfect matching didn't really work well. So obviously this became very slow, and like for lower physical error rates, we just didn't have kind of enough data to show, because the error rates, the error probabilities were so very, very low, and 10 to the 9 shots were not enough to conclude anything essentially. So that's why we have only data for this range, but from this we can kind of conclude a trend that the time overhead certainly decreases if the physical error rate decreases. It's already at the quantum memory threshold, which is around here. It's at most 2, and it decreases, and also it decreases if we increase the stability patch. So we would expect that like at physical error rate peak was 10 to the -3 with large merge stage patches. For lattice surgery, the time overhead wouldn't be higher than 50%. But yeah, certainly we need to pay a price. And probably let me just finish with this proposal. There is another proposal using the rotated planar code, which I can show you after the end of the talk if there is a question about that. But we found that the tangled syndrome extraction method is particularly nice for the annotated planar code. So again, here is the QPU, the hardware. We laid this background lattice on top of the qubits, so every qubit is either in the middle of the square or at the corner. And so we laid out these patches in tie units. So this is a tie unit here. That you can see this distance 5 patches at the corners. We have some routing space here. You can see this dotted area here. This is where we can put elongated rectangles and twist defects. Otherwise, we just put local stabilizers. So now, if we would like to measure any Pauli operator, we can do this by one lattice surgery operations using the tangled syndrome extraction method, using just this connectivity. And this is something which we never seen before. So this is how it goes. So if we just care about one tie unit, then an XXXX can be measured like that. So you can see that these are the elongated rectangles which are measured with tangled syndrome extraction. And so these things you leave out essentially. And if you would like to measure ZZZZ, then this is how you measure. The purple dots are the ones which you have to multiply in together to get the outcome. And you can combine these templates. So if you just would like to measure Y on this patch, then you also include this these things here. If you would like to measure identity here, you cut out both this and that one so that you don't include this patch. And using these templates, you can construct an arbitrary Pauli measurement within one tie unit, and then you can merge them. So here is an example how you could measure an arbitrary Pauli operator. So this is a example of YY, identity Y, YYY, identity X, Y, Z, and so on, lattice surgery. So within each tie unit, we constructed the patches, the merge stage patches, and then we connected them here, there, and there to kind of have the very general measurement. So we also demonstrated in the paper that if we use tangled syndrome extraction here, then if the distance of the patches are D, then the distance of this merge stage patch is always at least D-1. So we lose one distance only with this method. Okay, I have another proposal for the rotated planar code, but let me stop here because I'm out of time. Thank you very much for your attention, and yeah, I'm happy to answer any questions or explain more if there is any interest.
Okay, thank you very much for the talk. It was a very nice talk.
Thank you.
I would like to extend a little bit of time. If you want to talk about your next proposal, face it as one of the questions. What is this this other proposal? And you can present to us while the audience thinks about some questions.
Oh, sure. Okay, I'm happy to present it if I just didn't want to go over my time, but if that's okay, I can present. Yes. Okay. Yeah. Thank you for giving me more time for that. Yes. So essentially, just to recall, this was the twist-free lattice surgery method which Chamberlain and Kimball introduced in their paper. And so we kind of propose a very similar method. So the method is based on kind of a mixture of the previous proposal and a mixture of this twist-free proposal. So what happens is that, like, so once again, if we want to measure an arbitrary Pauli product here, we initialize an auxiliary patch in 0 state and then do 2 rounds of lattice surgery. So we can lay out the patches. For simplicity, we chose to have square-shaped patches here, but we could have rectangular-shaped as well. And we demonstrate how the method works with the same X, Y, Y, Z measurements. So this is a tie unit, and we just kind of have many tie units next to each other, like in the previous paper. And the connectivity we use is this one. Then, so like here, we can initialize the auxiliary patch. So we don't have to initialize it at the boundary, let's say like before. We can initialize it in the routing space. And therefore, in our proposal, we need shorter merge stage patches. So we initialize this somewhere in between 2 logical patches. And then just perform essentially the first X type lattice surgery with this patch. And after that, we just perform the second step, which would be Z X type lattice surgery. So Z X type lattice surgery. So again, because this is a mixed type lattice surgery with patches which are aligned with respect to the background lattice, we somehow need to compensate for that. So here in this column in this column, we use tangled syndrome extractions to measure these elongated rectangles, essentially. So these are the lines here. And sorry, it seems that for some reason there are no lines here, but there should be lines here. So these are also tangled, measured by the tangled syndrome extraction. So these should be also tangled. But the purple ones, which you multiply together to get the outcomes. And then, of course, you finish by measuring this out. And then you performed twist-free lattice surgery with 2 numbers of rounds. And if you use this, two lattice surgery operations, for the first one, for this one, you need the same amount of number of rounds as usual. For this one, you need maybe, like, let's say 50% more rounds. So I would say if we execute this, then this means we need 2.5 times more rounds. Sorry, not 2.5, 1.25 as compared to twist-free lattice surgery, and 2.5 times more if we just compare it to the case when we don't care about connectivity constraints. But this measurement can be also performed with just 1 round of lattice surgery in this case, which is not always the case for an arbitrary Pauli measurement with the annotated planar code. But for this specific one, which was the example from the Chamberlain-Campbell paper, it is the case that we can do just twist-based lattice surgery. So we just measure X, Y, as you can see here that the patch is connected with both X and Z boundaries. Here we connect with Z boundary, and here again we connect with both X and Z. So we can, using twist defects and elongated rectangles here, and also here twist defects and elongated rectangles, we can measure with just 1 lattice surgery operation this X, Y, Y, Z, X, Y, Y, Z Pauli product. And this would require 50% more number of rounds during lattice surgery because of the time overhead. But essentially, the conclusion would be that like the twist-free lattice surgery method would require taking into account hardware constraints and modifying the hardware with this dislocation area would require twice as long time. And with this proposal, we don't need to modify the hardware, so we can do it on the square root connectivity device. And if we assume that like half of the measurements can be done via this twist-based proposal, and the other half have to be performed by twist-free proposal, then we get the same time overhead. So we have to spend twice as much time like in the twist-free paper, but without modifying the connectivity of the hardware. So in the rotated planar code case, this is the conclusion that we have the same time cost and in the as in the Chamberlain-Campbell paper, but we don't have to modify the hardware to get the same performance. Yeah, that was the other proposal.
Okay, very nice. Thank you.
Thank you.
Does the audience have any questions?
Hello.
Hello.
So thank you for your talk. But I'm not quite familiar with the error correction, but I want to ask usually what's the so in the setting usually the circuit is fixed and for during different run, so you just arrange different page from run to run. So you just need to reconnect the qubit. So is that true? So is it easy to implement in the real case? So you need to arrange the page from each run, right?
Say that again. You need to arrange or what did you say?
I mean,
That again, sorry.
from different run, so do you need you have to rearrange the page for your purpose, right?
No. So what do you mean by rearranging? So I like let's say if you would like to measure this, then like essentially if you choose the Pauli operator you want to measure on this logical qubits, then just these merge stage patches are different. So you will have to define different merge stage patches, but the qubits themselves, the logical qubits wouldn't move. If I'm not sure if that was the question, but so they are fixed. They are located on the hardware. That it is qubit 1, qubit 2, and so on. And all you do is that whenever you have to perform this multi-qubit Pauli measurement, you just based on that information, just define this merging stage patches for lattice surgery. Yeah, so the qubits don't move in this sense.
So when you mentioned merge, so how do you merge them? You use additional gate to connect them. So
yeah.
Okay. So you need to apply new. So it's from run to run. You need to merge the arrangement. So the purpose of different run is to get different measurement result, or what in your scheduling? What's your the purpose of from run to run? What's the purpose of getting different Pauli measurement result, or you need to do
so
it?
for taking different Pauli measurements, but it was the motivation for that. Yeah, I have to go back to this slide. Just a moment. I try to find it. This one. So essentially, we always start with a circuit which has T gates. So the T gates are the green gates. The orange ones are Cliffords, and the blue ones are measurements. And you transform into a circuit which essentially contains magic states, and then this blue multi-qubit Pauli measurements. So your circuit will be preparing some magic states and then execute these blue boxes. And each of these blue box is a lattice, is like essentially all what happened in the proposals is to show a method how to measure these blue boxes. So let's say here in the Chamberlain-Campbell paper, the blue box would be X tensor, Y tensor, Y tensor, Z from this slide. And once you kind of said that, okay, I would like to measure this X, Y, Y, Z, then B, C, D is the proposal to do that. Yeah, so always essentially what you have in you can transform your circuit into a series of multi-qubit Pauli measurements, which can be very arbitrary. Like it could happen that let's say all your logical qubits is involved in the measurement, and this paper and the other paper, the twist-free paper, and also our paper was about to define ways how you can actually do these measurements using one or two lattice surgery operations. Does that make sense? Or
So that's for single run.
say it again, sorry.
This is for a single run, right? And how about the scheduling for different run? You just need to see what's the measurement you want to make for each run, right? Okay.
Yes. Yeah. But but I think like scheduling, you mean like which measurement to execute first, or do you mean something else?
I mean, so your proposal is like to see how to implement all these different Pauli measurement for each run, but the scheduling of them is a different thing, right? If it's not related to how you patch them, or you just decide the scheduling.
Oh yeah. So you okay? You mean like how? Okay. So do you mean like how to construct the circuit to measure this?
Yeah. Okay. Yes.
That's what you mean. Okay. Yeah. Yes. So this I didn't go into the details, but for let's say these ones here. So for the annotated planar code, it's there are two choices usually. If you just concentrate on the on the patch itself, then maybe let me just show you in the first. So here, so for the annotated planar code, because so if you do this first, then that second, that third, that fourth, or you can do 1, 2, 3, 4. So in like a lightning bolt shape. It doesn't really matter which one you choose. So you can just do this shape for both types of plackets, because then you spread the error in this diagonal fashion, like diagonal way, and they will not harm the effective distance in the annotated case. So in the proposal for lattice surgery, which is here, let's say, what we just said in the paper, that we would schedule each placket in this lightning bolt shape, and like you can kind of, let's say, just reflect along this diagonal line the scheduling to get it tangled, and that would work in 4 layers. For the rotated planar code case, which is so this one, you just use the standard scheduling for, because these are local stabilizers. So here you need 4 layers and tangling layers. For this one, we found only a way where we needed 5 layers instead of 4, because we had to insert idling layers to accommodate the tangling. But you can always do it with the 5 layers. So kind of you just use the scheduling which you have usually, and then here you kind of change it in a way that these column gets entangled, gets tangled. So if I go back to this picture, not this one, sorry, this one. so this picture here, you can see the numbers, and in the paper we kind of explain that if, let's say, this part here is at the middle of the patch, like let's say lattice surgery, then so what you do is that, like, here you have a Z-shaped scheduling on the blue placket and N-shaped on the X placket, and they are numbered from 1 to 5. And they are so because here in the tangled version, we needed to use like this N-shaped for both. And then below, you can just continue with like reflecting this scheduling. So you can always insert this into the middle of a patch to do it in 5 entangling layers. So the only thing that happens with these 5 entangling layers is that, like, each qubit is still involved in 4 entangling layers, entangling gates, but they are a bit more idled. But still, it's a load-up circuit essentially. So this is how you can. This is the scheduling you can use for the merge stage patch for the rotated planar code case.
Okay, I see. Okay, thank you. So another question is, I noticed that in the after measurement, the blue color you showed earlier, there are still some circuit. Why after measurement you still have other circuit?
So you mean this one?
Yes, yes. Like after the blue color, you still have other things. So what's the purpose of after measurement?
After these ones, you mean?
Yeah. For example, there are 3 column of blue, but you only measure the Y, Z, Z, Y. And how about the after one? You do them for the same run, or you do them separately, or what's the, or you do them all together? What's the difference?
Yeah, so the difference is that you do them one after the other, essentially. So in this picture, if this is your transform circuit, then let's say if we start here, then you do this one, and after that you can do this one and this possibly simultaneously. I mean, in this case you can do it simultaneously. Sometimes you cannot, but like typically it depends on the layout of the patches, like whether you can merge the 2 set of patches in a way that they don't have to cross each other. But like you can always just say, okay, let's do this one first, then that one, and then the other one, and the other one. So you can just go sequentially. And sometimes, if it's possible, you just combine some of them in the same round. But you can think about it like you just do each Pauli measurement sequentially. In general, I would say for a very general algorithm, if you convert it into such a circuit, I would just go one by one. And there is subtlety here because you have to first do these green boxes, which are blue boxes, and then some corrections. So if you do this first, then this Clifford and Pauli correction will affect this because they are not actually executed, but they are pushed into this measurement, so they will change the basis here. So typically in a general scenario, I would say do one of these blue boxes, then if it's a green box, you will have some orange and gray boxes, which then you combine with the next measurements, which will change the basis. So I would say, yeah, each box is probably one step, I would say, in general, just to be on the safe side.
Okay, so basically they do not appear altogether. You just choose one to measure.
Yeah.
And it depends on how you arrange it.
Sorry?
Sorry, you continue. Sorry.
No, I interrupted you. So sorry.
I just say so basically they do not appear simultaneously. You just choose them, but it depends on how you arrange them. Like you say, for some cases it will affect the other ones. Yeah.
Yeah, exactly. So like here, once you have this circuit with green and blue boxes, that pretty much fixes the order in a sense that like you cannot execute this before this one, but here you can choose, and that would then of course change the rest of the measurements. But yeah, so I would say once you have this picture here, you just go one by one and do them.
Okay, so just want to make sure. So this is all for single run for the certain type of merging, right? Correct?
Yes.
Okay, I see. Okay, thank you very much.
No problem.
Hi. Sorry. So here the green and blue. I just wonder, like, the circuit here is to error correct the qubit only for that, or is like like after I doing this green operations, and then I do the the blue measurement, so I can guarantee I can error correct the errors in those logic qubits. Is it true, or how do I understand these operations here?
Yes. So yeah, when you have your circuit compiled to Clifford plus T, which is this one. So at this point, you don't really do any error correction.
Okay.
But then you transform it into this picture, which is still like just this picture, or this circuit itself doesn't imply any error correction, but you execute all of these steps with in an error corrected fashion. And this is done by lattice surgery, essentially.
Okay.
So lattice surgery is the method to execute these green and blue boxes in an error corrected fashion.
Okay, so here this is just maybe some algorithm or something operation you want to implement, but the error correction part is by the lattice surgery.
Yeah,
so
exactly. Yes.
Okay,
yeah.
Okay. So I have another question is, so in the when you talk about the lattice surgery, and there are different patches, but why there are some patches is further away and some are more close? Because I mean, imagine if you want to do the lattice surgery, maybe you want them to be as close as possible, then you have to do less operations, but maybe you want to keep some distance for the crosstalk noise or something. I don't know. So why? Yeah.
Yeah, that's a good question, because like usually, let's say if I go to this case here, usually what happens is that like you have the circuit, then you allocate the logical qubits into patches, and yeah, and kind of you sort of fixed how distant are they. I guess you can, once you have the circuit with multi-qubit Pauli measurements, you can maybe do some optimization, but the Clifford corrections will always modify the Pauli basis, and like they could increase the weight of the Pauli operator which you measure. So I'm not sure how much you can optimize them. I think on superconducting hardware, you just have to live with the fact that you might need these long merge stage patches.
Okay.
Yeah, which of course means that the longer the merge stage patch, the more chance there is to have a logical error in the end, so that we cannot correct for that. And one reason why, let's say, we think that this, when we compare to this proposal where we always have to connect to this part here where there is the dislocation. So this proposal is better in a sense that we can initialize this auxiliary patch anywhere. So if they are here, and let's say around these, there would be like thousands of other patches, then we don't have to initialize this like at the edge of the hardware, but we can initialize it in the middle as well. So this means that we have shorter merge stage patches. potentially in this proposal. And this is a consideration, of course, like if you have a very long merge stage patch, then probably if you really want to sure that your error corrected procedure will work, you would like to have tall patches, or like you have to probably increase the distance to compensate for that. But if you can use shorter patches, like in this proposal, then it's less of a concern, I would say. But still, of course, it could happen that like I want to measure like an X, Y, Y, Z, which are, let's say, these Paulis are supported on patches which are far apart from each other.
So do you like have some estimation of like how many physical qubits you need or something like that? Because it seems a lot.
Yeah.
Just wondering. Yeah.
So like in general, it of course depends on like how noisy your hardware is, but like just let's say if we are well, it's hard to tell in a sense that like it depends on how many patches you have, but like if let's say so I don't have like concrete numbers, but like if you would like to have like a patch, just one quantum memory patch, which sorry, one logical qubit, which can survive a trillion quantum operations, then if I remember correctly, for physical error rate p equals 10 to the minus 3, I think you need like 20 by 20 patches probably, or maybe 25 by 25. Yeah, but like you know, that means that like if you have physical error rate 10 to the minus 3, and in the logical patch you want 10 to the minus 12, so that's a big improvement. For that, yeah, probably like 1,000 qubits is needed for one patch. Yeah.
Okay.
So it's a lot of qubits.
True.
So could I ask, so you say that the auxiliary patch should be close to the qubit that you want to measure? So how to choose the?
Yes.
Yes. Okay.
Yeah. So it's I would say that like in this scenario where you have the patches like that, you can just like, let's say in 3 columns, you can just initialize it in the next column between 2 logical patches. And this typically could be the case that you just initialize in the next column. If you have like in a few columns you have these Paulis. But like it might be also possible, like let's say if they are far apart, let's say there is one here, but this Y's are, let's say, here, then I would probably put the auxiliary patch here. So essentially, I would say probably any column where you don't have any Paulis is probably would work.
Okay, I see.
Okay.
Let me ask another question. So so the procedure would be like so when you want to do some certain operation, so you encode your batches in a certain way, but then later if you want to do some other operation, then you have to maybe initialize them, then encoding then each page to another way, then you do the lattice surgery. So is it like that?
Sorry, can you repeat the question?
I mean, if you okay, so like if I want to do some operation, so I have to encode my patches in a certain way, and then if I want to do some other operation, so I have to initialize them, then to encoding them to another way. So like if I want the operation will keep like, okay, encoding and initialize and encoding and initialize something like this?
You wouldn't, so you would only initialize this auxiliary patch, but if I go back to the, I'm not sure if, let me just say this, I'm not sure if this answers your question, but like once you have this, you start with initializing these patches, and then you don't reinitialize them, if that makes sense. So you kind of want to keep these patches alive until the end of the computation. So so the reinitialization of patches would be only for patches which we would use for, let's say, twist lattice surgery, or for some other reason, like if you want to perform a CNOT gate, for instance.
Okay, maybe my question is more like, so I have like logic qubit here. Then if I want to impose doing some like logic gate on the logic qubit, then what it would be like?
So essentially the logic gates are here in the first steps, and so you could sequentially execute these gates. For that, you need a method to do the T gate, which is sort of here. But you also need to have a method for controlled X operations, which is this one, and this is like a square root of X gate, dagger. So you need like procedures to execute these Cliffords as well in a logical fashion. So that certainly could be an option, but like here in the talk, we kind of consider just this Pauli-based computational model where like this circuit essentially becomes like a series of blue boxes, which are after each blue boxes, the rest of the blue boxes will change because of these corrections. So kind of this means that like with this proposal, you can combine many of the gates here into just one blue box. So you have less of them, but you could certainly, do these things sequentially. But then you need a process to do all the logical gates, which is possible. So it's kind of a possibility to do that. But this typically would take, but in certain cases when you have limited magic states, this would take less time. And therefore, it's a popular proposal to consider in costing papers, resource estimate papers. Sorry, but yeah, like it's I think probably when we have like I don't know 1 million qubits at some point, and we can do these circuits in an error corrected way. I think probably each algorithm will require a decision before we execute, whether we do it this way or that way, or something in between. And I think probably something in between would be the general approach, that like some of these gates you would just execute because you could do them quickly, and other you would combine into such blue and green boxes. But that's just my feeling.
Okay, thank you. It's nice. Yeah.
Thank you.
Okay. I think that's all for the questions. So let me thank you once again for accepting coming here, talking to us, giving us a very nice talk, and a lot of answers as well.
Yeah, thank you for the invitation.
Let me stop the recording.